So Rodolfo, who made the logo? It's really nice.
I made it.
Oh, cool.
And it's completely done in Keynote, which is a little bit.
Hey, it doesn't matter.
Okay. Hi, everybody. Thanks for joining us today for the third session of this week on solar system objects. We have 3 more sessions after this session for this week. The next one is this later today at 11 on communications and coordination, a panel discussion. And then on Friday, we have 2 sessions, one at 9 a.m. and one at 11 a.m., both of them on massive and evolved stars. I hope you can join us for those. Today's session is on solar system objects, and we have 3 speakers today, 2 invited talks and a contributed talk. The first speaker, I will introduce them and you can start sharing your slides. Our first speaker is Dennis Bodewits from Auburn University, who will speak to us about time domain studies of solar system X-ray emission.
All right. Can you confirm that you can see my slides and can hear me?
Yes.
Wonderful. Good morning, everybody. Thank you, Rodolfo, for the invitation to speak in this meeting. I'm going to give a sort of broad overview of solar system X-rays and how and why this is interesting as a function of time. This will be followed up by Damien, who will focus more on comets, and by Will, who's going to talk about Jupiter, which is probably one of the most complicated environments. Okay, so solar system X-rays. You've already had a couple of days of this meeting now, and we were preceded by the X-rays of planets and disks and stars, and the solar system is an extension of that. The nice thing about the solar system is that it offers a really broad range of environments, from the giant planets to the rocky planets and to objects as comets that move around. The X-rays from the solar system come from very different X-ray emission mechanisms, and of course, as physicists, that is where we perk our ears. In combination to remote observations, some of these objects have been visited by space missions. Space missions can provide local measurements of magnetic fields, of particle environments, and as you will probably see from Will's talk as well, remote observations are really important to go along with those space missions, because space missions by necessity only measure very local conditions, whereas your X-ray observations from Earth orbit provide the macroscopic context, the large-scale interactions. solar system observations are very much embedded in time domain studies. There can be orbital or seasonal variations. The sun, which is a driver of many of the X-rays from planets, it varies on timescales from minutes to years, as we'll see. And also, solar system observation are often provide opportunistic events. So those can be missions, but there's collisions, there are outbursts, there are specific alignments, there are specific apparitions of objects that are interesting. So let's have a look at some of those. So we need to start with the sun, and this is a beautiful image of the sun, which is a combination of SDO in soft X-rays, that's the red, and new star hard X-rays, that's the bluish green observations that you have. The sun, our closest star, emits X-rays because of bremsstrahlung and collisions between ions and electrons in its atmosphere. X-rays are typically of order of about 1 million kiloelectron volts. That's the soft X-rays that you see here at 171 angstrom. And harder X-rays, where it's a relatively soft source, and that's the new star observations, and that's a couple of million kiloelectron volts. Just to show you a little bit about temporal variations of the sun. So first of all, we have solar flares, brief enhancements of in solar brightness. It's shown in the bottom right there. Those flares, you may know, there are different classes which are related to both their spectrum and their intensity, and they can last tens of minutes. Then the sun also emits a plasma, which is called the solar wind, which is a particle stream of mostly hydrogen and electrons. At the distance of Earth to the sun, it's about 1 particle per cubic centimeter. And embedded in there is also our helium ions, as well as heavier ions, carbon, nitrogen, oxygen, the ones that are most abundant in the sun. The properties of the solar wind are summarized in this somewhat. Can you see my mouse? Yeah, I think you do.
Yes.
In this somewhat complicated plot over here, this is a summary of data acquired by the Ulysses orbiter, which went around the sun in a polar orbit. And it measured the solar wind speed, which is indicated by these lines here. And what you can see is that around the ecliptic, the equator of the sun, the solar wind velocities are relatively low. Whereas if you go about 20 degrees of latitude or higher, solar wind velocities pick up to about 700 kilometers per second. This organization disappears around solar maximum. We have a lot of outbursts, and you can see it's just an enormous chaotic mess by then. These different solar winds also have an implication on the composition of the solar wind. The equatorial solar wind has an overall higher abundancy of highly charged ions, whereas the polar solar wind comes from cooler regions of the sun and therefore has less highly charged ions. And of course, this varies with the solar cycle or 11 years. So you have a really large span of variations here, again, going from those flares that last minutes to solar cycle events which last a decade. So I'm going to go through some of the, I'm going through our solar system. This is going to be an X-ray tour of the solar system. And of course, we have to start now with Earth. Chandra, in fact, has observed Earth, which I think is spectacular. And these are observations that were analyzed by Neil Bartwai, and he summarized them in his paper here in 2007. On the left, you have Earth, and what you see is an aurora. And Earth's aurora is mostly caused by particles accelerated in its magnetosphere. And so you have two emission processes. One, these are ions that can collide with atoms and molecules in our own atmosphere and get excited. And second, you'll have continued emission from bremsstrahlung when those particles are decelerated. The moon on the right has also been detected in X-ray. What you have here on the left is the first quarter. Remember from your astronomy classes, you can draw a P there if you draw a line. So that's first quarter, and this is if you can draw a line up here, dernier, that's the last quarter. So in fact, it's the illuminated part of the moon that is brightest in X-rays. So the moon is reflecting those X-rays. Lunar missions have used this to analyze the mineral content of the moon. We don't quite have the sensitivity and resolution to do that. What you also see is that there are a lot of photons in front of the moon, not as many as behind it, but in the dark side of the moon, there are X-ray photons. And this has, of course, long been subject to debate, but the current understanding is that these are particles that interact. So it's a solar wind interaction with the Earth's exosphere. So mostly hydrogen that is at high altitudes, and you get charge exchange reactions that emit X-rays. And this is important because it causes a soft X-ray background also for anybody who wants to look at objects that are further away. The X-ray of the emission of the Earth is going to be the subject of two small sats that are about to be launched. On the left is the SMILE mission, which is a collaboration between the European Space Agency and the Chinese Space Agency. It's a relatively large mission. Cupid, led by Boston University and NASA Goddard, is a small sat, and that will also look at the Earth's X-rays to understand the Earth's magnetosphere's interaction with the solar wind. So these are both two space weather missions, and this is something, of course, that when charge exchange X-ray emission was first discovered, would have almost appeared like a miracle. Next up is Jupiter. Jupiter is one of our brightest X-ray sources and by far also the most complicated. So Will's going to talk about it much more. It's a perfect time domain object. It varies again on many large scales. There are processes such as the aurora shown in this stunning image here, both on the North Pole and on the South Pole, which are driven by different mechanisms. Particles are accelerated in Jupiter's strong magnetic field and participate down. Yeah, I'll leave it like that, so just not to steal Will's thunder here. Saturn. Saturn, being so much farther away, has been detected in X-rays, but it was an extremely hard object to catch. The emission from Saturn seems to be simpler than that of Jupiter. That may be because we haven't been able to study it in as much detail. Most of the X-rays from Saturn seem to come from the disk, so not from the famous rings, and they seem to be scattered solar X-rays. And this was confirmed by the beautiful time domain study here. What you have here is in black the X-ray brightness of Saturn as a function of time, and this is hours. And then this is compared to the solar X-rays measured by the GOES satellite and by timed here. And you see that this solar flare that was observed between 7 and 8 o'clock is perfectly visible here in the X-ray emissions from Saturn, confirming again that the bulk of Saturn's emission is from scattered solar X-rays and not any magnetospheric aurora processes. Venus. You can count the photons in this image acquired by Conrad Daniel using Chandra. So this again poses a really challenging observation. As you know, Venus is inward of Earth, so the geometry is not beneficial, and Venus can only be observed at very limited times. Venus is a very faint X-ray source, and just like Saturn, most of those X-ray photons, they come from scattered solar photons. Next up is Mars. Mars is a very interesting X-ray source, and it was the subject of study by Conrad Daniel again, both with Chandra and with Exum Newton. So in the left, you see an X-ray image of Mars that was acquired with Exum Newton. The circle in the middle is the disk of Mars, and you see that the X-ray emission is much more extensive than just the disk. And so these two spectra then on the right are first of the disk. This is the one here, and this is of the halo. So that is the exosphere of Mars. So the disk is, again, most of the photons come from the disk are scattered solar photons. And what I want to point out is this very bright line in the middle, which is, I think, the only molecular emission that we've ever seen in X-ray. These are photons scattered by CO2 molecules in the atmosphere of Mars. then the spectrum of the exosphere of Mars looks very different. And this is a typical charge exchange spectrum with those very strong forbidden oxygen lines being represented here. So what happens here is that you have, and I have the line identification up here. So line 9 and 10 are the CO2 lines, and lines 6 to 8, so again, those here in this amber color are the oxygen 7 forbidden intercombination and resonance lines. So we'll see that again when we look at comets, but we know that they are the signature of charge exchange. So what happens here is that you have this atmospheric escape from Mars where CO2 is photodissociated, breaks up into atoms. Atoms are found at large distances away from the nucleus and can be eventually, when they're ionized, be picked up by the solar wind. When the solar wind interacts with those neutral atoms, they will capture electrons and emit in X-rays. So that process is summarized here. So you have your ion coming in red here with a charge Q+. You have a hydrogen atom here with an electron orbiting it. At some point, these two particles are in a quasi-molecular state where the two nuclei are close enough together that the electron orbits both. This, of course, is a very brief moment, and the electron has to decide whether it stays with its old friend or goes along with this new romantic partner. And in this case, the electron is captured here by the incoming ion. This motion here indicates that it's captured into an excited state. It drops down to the ground state and it emits those diagnostic X-rays that we just saw. Just some properties from summarized below here. So the solar wind, which I introduced when we were talking about the sun, is caused by a 1 or 2 million degrees Kelvin plasma. In the solar system itself, it's collisionless and it's moving around with velocities typical of between 300 and 1,000 kilometers per second. And again, it's highly variable. You will have multiple shocks. It's typically variable on hours to days. You have smaller shocks moving through it in hours. You have larger CMEs that can take about a day or a few days to pass through a system. Charge exchange typically results in soft X-rays below 1.5 kilo electron volts in our solar system. That is because of the ions that you have available in there. So that's directly coupled to the temperatures in the solar corona. It mostly interacts with simple molecules in planetary atmospheres. Water, CO2, H2, helium in the background, and its prime diagnostic, you will see again, are the forbidden lines of oxygen 7 at around 560 eV. So just to linger on Mars a little bit. Recently, the group from the University of Georgia, they demonstrated that if you have charge exchange emission from oxygen 7, you're going to get different line ratios between the transitions between the 2 to 1 levels and higher levels, so the K series. And so an example here is what you get from charge exchange of oxygen with CO2 in red and with oxygen, atomic oxygen, in green. And again, notice here that this line is much stronger in the case of CO2 with respect to the forbidden intercombination and resonance line here, whereas in the green case, this system is much stronger than the higher order lines. So these are theoretical calculations. It is very difficult to do charge exchange experiments on atomic oxygen. Also in experiments, it's very difficult to measure the forbidden line because it has such a long, the state has such a long lifetime. The prediction is there, and that would mean that you can use X-rays from charge exchange also to measure local compositions. So does that work? To do that, I went back to Conrad's spectrum, and I showed the wrong one here because this is the disk one. I should have shown the halo one. And what I saw is that in the halo spectrum, the K delta was very strong, and that means atomic oxygen. And that is indeed what you would expect. Again, Mars itself, and that puzzled me at first. And let me explain you why. So Mars itself is mostly CO2. However, at higher altitudes, specifically the altitudes that were the XMM observations were, again, you have that exosphere where all your CO2 is destroyed, and you're left with atoms. And indeed, the spectrum that was measured by XMM is consistent with a spectrum that you would expect from atomic oxygen. So that's very promising also for these theoretical calculations done by this group. All right, let's get to it. I'm a comet man, so I'm going to talk about comets a little bit more. This is an image that was acquired by two instruments on Swift. So the X-ray telescopes, XRT, and the UV optical telescope, UVOT. So this is a very bright comet, Comet Lulin, and Swift instruments are always working simultaneously. So what you have here in blue is the molecular distribution of OH, neutral hydroxyl molecules. And in red, you see this pointy shape. Those are the X-rays caused by solar wind charge exchange with the neutral atmosphere of the comet. You see that the morphology of the two is very different. And the reason for that is that cometary atmospheres, especially of a comet as active as this guy, are collisionally thick. So you're gonna neutralize your solar wind ions, and when that's done, they can no longer emit any X-rays. So you have a morphology that is displaced towards the sun. How you can think of this is sort of like an umbrella in projection. So if you were to see the umbrella from the side, you see a hemisphere. If you see the umbrella from the front, you still see a circle. And this is somewhere in between, where the umbrella is about tilted by a degree of 45 degrees. Why are comets so interesting? Comets can do a lot of things that other planets don't get away with. So first of all, comets are found at different latitudes. Our planets are confined to the ecliptic plane. Comets can come in at different inclinations. So that means that, thinking what we said about the sun, that you have during solar minimum, you have this organization with respect to latitudes. Comets can also sample the polar solar wind, which is a solar wind that we don't get to see much because it takes a lot of energy for a spacecraft to get away from the ecliptic plane. Furthermore, comets get to move around the solar system, so you'll see them at very different heliocentric distances, sometimes even very close to the sun. This also affects the comets themselves. Their activity levels vary greatly. That's easy to understand. When a comet gets closer to the sun, it gets hotter, so the ices in it sublimate more. The second thing is that comets are a good analogy to planets without a magnetic field, so just like Mars and Venus. However, they are very extended sources because their atmospheres are not bound. And so that means that you can study things as a function of distance. You can study different plasma interaction regions. You can study their bow shock, and you can also study different enhancements in this local atmosphere. Temporal variation, most of their temporal variation is driven by solar events. So we already saw solar wind variations. We know from the Rosetta mission that flares also have an impact. What this does for comets, we're not quite sure. The thing with flares, of course, solar flares, is that you have to be lucky for one to go off whenever you're observing. And then finally, and I'll show that in more detail, there's a lot of things that you can do with spectroscopy. So that's first of all, you can sample the solar wind and then tie it back to the origins of the solar wind on the sun. You can study the forbidden lines, which we can't even do in a lab. So comets as a physics lab. Just as for Mars, we now have the hope that we can study the neutral composition of comets in X-rays, which is great because molecules like CO2 don't have a dipole moment, and you can't really study. CO2 does have a dipole moment, but you can only study it in infrared wavelengths, so not from the ground either. And it's still an open question what the dust around comets does to the X-rays. In a little bit more detail, this I like to call one of the most complicated plots in the world. There's a lot of stuff going on here. What we have here is X-ray observations of Comet Tempo 1. Tempo 1 had the misfortune of being the target of NASA's Deep Impact mission, where we shot a copper bullet in its nucleus to see what it would do. And in support of that, it was observed by Swift and Chandra for at least 2 weeks. So in the top plot, you see X-ray data. So those are indicated by blue for Swift and indicated in black by Chandra. So you see at least an order of magnitude of variation in the X-ray brightness here. So where does it come from? So in the second plot here, this is the solar wind flux. So the bulk velocity times the bulk density of the protons in the solar wind. And you see that they varied a lot in those 2 weeks, with a peak here, which is associated with a coronal mass ejection that's actually imaged here by SOHO when it set off at the sun. And this is the time where it got to the comet. Second, this comet was variable as well. It had a large outburst here caused by the comet itself. I labeled it, and this is the outburst smaller here caused by the spacecraft that were crashed in the comet. So now the X-rays are simply the product of your solar wind flux times its ion content, which is not shown here, times the comet gas production rate. And that's the light gray curve over here. And you see that the light gray curve does a very good job of explaining the X-ray brightness. So comet X-ray brightness is again, it's variable on these different time scales. You see this comet outburst, which is a few days. You see this coronal mass ejection here, which just lasts almost a week. And this allows you to study again the comet environment in very different conditions. Quiescence, comet outburst, where you enhance the local gas density, and plasma enhancements, where you probably also change the ion content of the solar wind. Chandra has been an amazing instrument to study a larger number of comets. And what you have here is about 8 spectra of different comets. The names of the comets are indicated by those phone numbers here. It doesn't matter so much. What you see here, when you let your eye go from the top to the bottom, that those spectra are very different. And the main difference is that the average energy of the spectrum shifts to the right, meaning the spectrum gets harder. So why is this? To study this, we did a typical astronomy thing, which is we defined 3 color bands. So you have this color band between 200 and about 450 EV in dark blue. You have
3 minutes.
Lighter shade up to about 600 EV, and then the harder the red shade for higher ions. So these corresponds to carbon and nitrogen in dark blue, oxygen 7 in light blue, and oxygen 8 in red. So what they mean is that these spectra are now organized along the solar wind freezing temperature. So what is the solar wind freezing temperature? The freezing temperature is the rate is just the local plasma conditions, and the hotter the local plasma conditions in the sun, the higher charge your ions will have. That's the ion ratio measured from the comets is shown in here. These are different solar wind regimes. Here you have a plot of the local temperature in the solar corona and the ionization fraction of your different ions. And again, the shaded regions, so typical solar wind regime. So you see that in your normal solar wind, most of your ions are going to be oxygen 6+, which do not emit in X-rays that you can detect with Chandra. They're all below 200 EV. But as soon as you get a little higher, you're going to get a significant fraction of oxygen 7+ and 8+. And so you see that these fractions, they cross these different solar wind regimes. So Chandra is very sensitive to local temperatures in the sun that cause the solar wind to vary. Carbon, not so much, because most of your carbon is in carbon 5+ and 6+ anyway, so you expect less variation here. So these variations in the spectra are mostly driven by more oxygen being available to emit X-rays. So a puzzle that was first seen by Damien is that there is significant high ionized silicon and magnesium in some cometary spectra. And as you see again from the same temperature versus fraction plot, it's not supposed to be there. Simply the solar corona does not have temperatures high enough to produce those ions. Yet we're pretty sure that we see those ions in cometary spectra. And as it was pointed out by Brad Sneos, this is a big puzzle, and maybe this is caused by solar flares being reflected in cometary dust. And this is a very active field of research yet. I'm wrapping up here. Farther afield, their X-rays may provide a diagnostic of planets and comets outside our own solar system, and you already had planets yesterday. So on the left here is our closest hot Jupiter, HD 189733, and Chandra was able to detect this planet transiting its star. So the star itself is the object here, and one of them is a binary star that is nearby it, and the other one is a background star. So this planet is really blasted by X-rays, and it loses a significant fraction of its atmosphere because of that. Then on the right is an artist impression of a gamma ray burst known as the Christmas burst. And at some point, it was suggested by Sergio Campana that this gamma ray burst was really strange. Its spectrum was strange. It lasted really long, and it was at first interpreted as maybe a large small body, something like Ceres, being disrupted by a neutron star. Since then, there's been a lot of papers about it, and especially this paper by Thuene et al. Suggests it's probably just a star being disrupted. But of course, we know that small bodies are falling on stars. We have that here. They're known to pollute white dwarfs, so it is a very likely mechanism to happen. But whether it would result in any X-rays is an open question. All right, so I can imagine that after seeing all this exciting stuff, you want to go ahead and build an X-ray telescope for us. So if you want to do that, here's our wish list. So first of all, we want to have high spectral resolution, and I think everybody on this meeting agrees with that. That we can't wait for the calorimeters to go up. For us, soft X-ray sensitivity is very important. So that this oxygen 7 lines at 560, but we really also like to extend that to about a quarter of a kilo electron volt. If we may, tracking would be wonderful. It would make our life much easier, specifically for comets that are moving pretty fast. A big problem that we've had, and I think Damien will touch upon that, is background observations. We deal with extended objects. And in other fields like infrared astronomy, it's quite common that you spend an enormous amount of time studying your background as well. Whereas in X-rays, that people get a little bit nervous when you spend a significant amount of time staring at nothing. We like optical blocking filters, especially Will looking at Jupiter, which is one of the brightest objects in the sky. More sensitive point, we need agile operations. Solar system observations are often driven by target of opportunity events. We have impacts, we have collisions, and we'd like you to be on target within days. Monitoring, please allow us to observe objects for longer times. Since many of the X-rays are driven by solar events, that makes them a little bit unpredictable as well. It's like the weather. And we are maybe not so good in predicting how bright our object will be. And one way around it is to allow for monitoring observations of about a week or 2 weeks, and then see the different conditions that the sun has. And then the final one, which is one of my pet peeves, archiving. Our objects don't have fixed coordinates. And so if you run your archive based on coordinates, it is very hard to retrieve our observations in that way. With that, I'd really like to thank you for your attention, and I would like to advertise that we have an open postdoc position at Auburn University, and this is in modeling and observations of atomic and molecular processes in cometary atmospheres, and it would involve the analysis of data by essentially every X-ray telescope, including NICER, which Damien will talk about next. Thank you so much.
Thank you, Dennis. That was an excellent talk. Very engaging. We do have a question from Brad Sinos. Great talk. Could you comment on recent high energy ExoComet studies, such as the swift observations of Borisov? How similar are these objects to our standard solar comets?
Oh wow, that is so cool. So that's in a completely new field. It has long been the holy grail in comet science to find a comet that was not from our solar system, but instead from another one. Problem was, we had no idea what to look for. How are they going to be different? With the first active comet that was discovered last year, 2I Borisov, we knew it had to come from another solar system because of its orbit. Its orbit did not close, so it had an eccentricity which was much larger than 1. and that was not caused by any interaction with Jupiter, for example. So we were absolutely certain that that object had to come from out of our solar system. It at first seemed to behave just like any other comet in our solar system, which in a way is not a surprise, right? If you heat a block of ice and dust, it's going to behave the same way, whether it comes from our solar system or the next. This object, however, was bright enough at about 17 magnitudes that people could start to do spectroscopy on it and really measure its composition. And so we had a big campaign with Swift and with Hubble, where Swift in the UV was able to measure its water composition and how this evolved when this thing orbited the sun. And Hubble was able to measure its carbon monoxide abundances in the UV. So both. So what was seen is that this object was shedding its outer layer really quickly. It lost a significant amount of water, and that probably exposed more primitive layers below. And those layers were very rich in CO. This comet had much more CO to ice than comets that we see in our solar system. And we interpreted that as that it was to come from a place that was much colder and darker than our solar system. I called it a snowman from a cold and dark place in one of the press releases. So maybe one of the theories that we have is that it came from an M dwarf system, so much cooler, CO snow line closer to the star, and still close enough that you are able to eject it.
Great. And we have a question from Huzen Song. How strong is the soft X-ray flux of corona and the coronal mass ejection? And can you separate coronal mass ejection from corona in the soft X-ray band? If not, how do you see the CME? Okay.
I'm not a solar physicist. Damien is. But so how we normally see them is there's a fleet of solar observatories at the first Lagrangian point, so a million kilometers away from us in a direction of the sun, and they measure solar wind properties, such as the bulk velocity and also the ion composition. So the CMEs have a significantly hotter ion composition than the solar wind background, and also a significantly higher flux and a significantly higher velocity. So they really change the resulting X-ray spectrum in planets and comets.
Great. We have one question that showed up in the chat from Ziyuan Li. Do you have a prediction for the number of comets detectable with eRosita?
That would be a wonderful question for Konrad Daniel, who's listening in. He did this with Rosat. So once the first comets, once X-ray emission from comets were discovered by Casey Liss from Comet Hyakutake, Konrad Daniel went back to the archives of Rosat and painstakingly looked up where there might have been comets in the sky, and he was able to detect a handful of them. It's all going to be about comets are. So the difficulty with comets is that they're bright, but they're also extended. So you're talking about low surface brightness, and so you can have a magnitude 7 object, but then the surface brightnesses are still very, very low. So you need to be a little bit lucky that you have an active comet at the time where eRosita is looking at it. Based on Rosat, I would think that we get a handful, but I'm not too familiar with their surveying strategy to know if it would really work.
Great. Thanks again for an excellent talk. I think it's time for the next speaker to start their slides. Our next speaker is Damien Christian, coming to us from California State University, and will talk to us about the analysis of charge exchange emission from Comet 46P Wirtanen.
Yeah, thank you. Let me just share my slides here. I just fear I would do this on mute. Can you see my first slide?
Yes, I can. Thanks.
All right, thanks. Well, let's get right into it. Well, I'm pinch hitting here for Emanuele, who's off in Italy. I thank the local organizing committee for including me and our work on comets, and it's been a long journey. I was at EUVE when Mike Muma saw 100 angstrom photons from Comet Hyakutake, and then of course Carrie Liss had discovered them using ROSAT. Collaborators, of course, Dennis and a few others here at Auburn and Dimitra. And also previously we've worked with Conrad and Brad and Carrie Liss. And so basically, I didn't make an outline because it's kind of a short talk. We're just going to present the results from our most recent COMET campaign on 46P Wirtanen, which was in December 2018 with both Swift and Chandra. And as Dennis mentioned, the solar wind charge exchange mechanism gives us a nice plasma diagnostic for looking at the solar wind and the exosphere of comets. Generally, these types of measurements were only available to in situ measurements. And of course, since it's an X-ray timing conference, we'll, there's lots of time dependence. As Dennis mentioned, the solar wind varies on timescales of hours to days. And of course, we have changes in the solar wind velocity, the proton density and fluxes, and of course, ion ratios. And early papers found sort of a good correlation with the X-ray emission and say oxygen ion fluxes. They weren't, cometary X-rays weren't so sensitive to variations in the solar X-ray flux. And then it showed the nice light curve from the campaign on a Comet Tempo 1 from the Deep Impact mission. And here's just a slightly different version. We're in the upper right. Let me see my laser pointer. Hopefully it doesn't crash my system here. In the upper right here, we just have the density as a function of days of the year back in 2005. This was July 4th is the day the impact happened. The solar wind velocity varied a lot from sort of a equatorial solar wind at a few 400 kilometers per second up to 600 kilometers per second. And then there's a plot of the ACE map of the magnetic polarity toward and away from the sun in red and blue. And we look at SOHO data also to see for any sort of solar outbursts that might affect the X-ray emission from the comet. And I also like to mention that charge exchange now has been found from galaxies. I think there's a paper on M82. It's been found in star forming regions, and also Hugh Hudson had a paper modeling, including charge exchange and solar flares. So it's been used in a lot of different fields. Oops, that one slide didn't show, but these are just a little from a while ago, our sort of picture gallery of comets we observed with Chandra, going from the one that broke apart, fragment B, from Schwarzmann-Bachmann 3 that I won't try to pronounce. I shouldn't have anyway, too early in the morning. There's Enki and good old linear S4 from the science paper in 2001. And so for 46P, we really had the exciting goal to try to map the sort of gas distribution in the coma. And Dennis also designed a really nice background. Since sometimes the comets fill the field of view for Chandra, we didn't want to have this uncertainty in the background subtraction. So we did 10 kiloseconds before the comet observation, 10 kiloseconds on the comet, and then 10 more kiloseconds on the background. And there was two different sets of pointings, December 3rd and December 13th, 2018. We also had hoped to sort of look at these X-ray lines between sort of 1 and 2 keV, and to sort of try to do more with the cometary composition. And here's sort of the observing parameters where Swift had 3 epochs. And of course, as Dennis mentioned, you get the ultraviolet simultaneously, where you can measure the water content or the OH. And so epoch 1 was in late November 2018. And epoch 2, which overlapped with the Chandra pointing, was in December 13th, and then a later epoch in January 2019. Just to point out, it was one of the fainter comets we've observed. The flux, although the flux was 11 times 10 to the minus 13 ergs per centimeter squared per second, it ended up being one of the fainter comets. We had 2 sort of 20 kilosecond pointings with Chandra, and 20 kiloseconds, 7 kiloseconds, and 14 kiloseconds with Swift. And so the disappointment was in the Chandra observation here, you can see these are remapped onto the coordinates of the comet. Kind of a crummy plot there, but the sun is sort of down to the lower right, north is up and east is to the left. And this is an image in 300 to 1000 EV, so the soft X-ray regime. And there's no sort of obvious comet. There's a little bit of excess from the early observation in December 3rd. And then in part 2, there's really not much, not an obvious comet either. So we were a little disappointed though, but fortunately for us, there is an X-ray spectrum. And then in the Swift epochs, you can see that in epoch 1 in late November, you can see comets and there's a nice X-ray detection. There was a slight detection in epoch 3 and then an upper limit, epoch 2. Then there's an upper limit for epoch 3. So we were pretty happy with the Swift observations that Dennis and Emanuele really were the key drivers for. So in terms of looking at sort of the solar wind parameters and the water production from the Swift UV, you can see here, this is similar to Dennis's plot for Tempo 1, where we have the X-rays with the Chandra being shown in green squares when the Chandra observations happen. So this is covering over a month of time. The smooth sort of, the blue points are the SOHO sort of smooth predictions for the water production. And then we have the proton densities. And of course, the first epoch for Swift is shown here as this blue shaded area. The Chandra is in green, and then the blue, and then December 13th, the Chandra and Swift sort of overlap. And this is the measurements of the proton density from both ACE and SOHO, solar wind velocity, and then the oxygen ratio from ACE. So unfortunately, the comet observations are kind of short, so we don't really see big variations, but we are able to measure the oxygen ratio from the Swift spectra. So here's the OH map, which Emanuele really worked on, and Dennis, I don't know much about it, but you can see that in the left panel, we have it was about 1.2 times 10 to the 28 molecules per centimeter squared, and then the contour is the X-ray emission overplotted on the OH map. And then you can see it gets a bit fainter as we go to later times. And so here's the nice Swift spectrum from epoch 1, where we fit it with sort of 3 broad Gaussian emission lines. The charge exchange models of Bodewits et al. And many others had too many free parameters really to model the lower signal to noise spectra. So we had lines around 390, 550, and about 680 EV. And then chi-squared was pretty low, 0.6 or something. So it was a really, really well fit with just these 3 emission lines. And like I said, a flux of about 11, 10 to the minus 13. And the Chandra spectra, well, here we had a little bit more of a difficulty. We had the nice background spectra from before and after the comet observation that we added together. You can see in the black is the comet spectrum unbackground subtracted, and the red is the Chandra background spectrum. You do have a bit of an excess here around 550 EV and maybe at 800 and some EV. So that was part 1. Part 2 is a little bit different. It shows a bit of a flatter spectrum, but there is a bit of an excess around 600 EV. And so that was part 2 in December. And if we do the background subtraction and we fit it with 4 or 5 broadened emission lines, you have sort of your carbon at 300 EV, some nitrogen, oxygen around 560. And there is sort of some excess here we attribute to neon at about 830 EV. And that was 4 emission lines. And then we had an extra component around 660 EV for part 2. And these are 1 sigma error bars, and the residuals, of course, the data minus the model is shown below.
3 minutes.
All right, thanks. And so We can sort of try to derive an oxygen ratio from part 2 of the Chandra spectra. But one of the things I wanted to point out is that as Chandra has lost some of its low energy sensitivity, so the red here is the Schwarzman-Wachmann model from Wolk, from Scott's paper 2009, showing this nice oxygen 7-8 peak here. I guess it's oxygen 7 at 560. We fold that model through the current response we used for 46P. You can see you're about 7 times less sensitive to the soft X-rays, so that you really are limited by a bit of degradation in ACES. Hopefully they can bake it out, but that's why we don't have a pretty picture to show, and the Comet spectra are a little bit weak. And so the ratios we got for the oxygen 7 to 8, 8 plus to 7 plus agreed well with the ACE and SOHO measurements. And we observed 46P in 3 different epochs. It was sort of one of the faintest comets. The flux was the luminosity was a few 10 to the 13 ergs per second. We have good agreement with the few measurements we made of the oxygen ratios, compared well to the solar wind parameters. We were a little disappointed that we didn't get more from the Chandra data, but it is what it is, and we're happy that we could sort of pull out a spectrum to at least fit some lines to, and hopefully in the future we can sort of continue on. We sort of thank the Chandra team for making many of these difficult comet observations, and that's it. So thank you. I'll take any questions.
Thank you, Damien. If we have any questions, please enter them into the Q&A box. And the speakers in this session, I just realized that you can't ask questions in the Q&A box. So if you have a question, feel free to raise your hand or enter it into the chat. Okay, we have a question from Brad Sinos. Given the reduced soft X-ray sensitivity of Chandra, would you consider SWIFT to be the preferred instrument for comet observations?
Hey, Brad, yeah, no, that's a great question. I think for right now, we're gonna probably, even though you don't get a spectrum for imaging, we might try the HRC on Chandra. And there's a few of those in the archive, but I haven't really made much sort of progress with them. But I think we did try Comet Atlas with the LETG, and it's sort of we're still working on it, but it doesn't seem like there's much there. And it was kind of a short observation that we got through DDT, but director's time. But yeah, I think for right now, for sort of the typical charge exchange spectrum that we've been working on, SWIFT might be a little bit better than ACES, but like I said, we're going to try the HRC next time, I think.
And SWIFT is not any bigger. The effective area is the same, and also they don't have an optical blocking filter, so there are some limitations there as well. It's a small telescope in the end.
Yeah. Thanks, Dennis.
I had a question about the image that you showed that you were disappointed with, I should say, the Chandra one. So the X-ray emission that we see there is or is not from the comet? It is from the comet. It's just not coherent in any way.
Yeah, it's from the comet. It's just not. It just doesn't make a pretty sort of Q-tip, crescent shape that we're sort of used to seeing.
Okay.
We had this problem for Comet Holmes. There's some X-rays there, but you can't really see the comet. Just doesn't jump out to your eye. But it's always a competition between the soft X-ray background and your comet, right? The background is rising pretty dramatically below 300 EV, so you can hit these things 100 times. Thanks.
Any additional questions? We may have time for one quick one. If not, thanks again, Damien. And let's have the next speaker, William Dunn, start preparing his slides. So our next speaker is William Dunn from the Mullard Space Science Laboratory at UCL, and will be speaking to us about revealing the processes that produce planetary X-ray pulsations.
Hi, can you hear me okay?
Yes, I can.
And can you see my cursor?
I can see your cursor.
Okay, perfect. Okay, so hi everyone. Yeah, fantastic talk so far. I really enjoyed them both. So I'm going to talk about, over the last 4 years, we've had these incredible campaigns with Chandra and with XMM that are synchronized with the Juno spacecraft. So Juno is busy orbiting Jupiter at the moment, and it takes these huge 53-day orbits that carry it from somewhere over the pole of Jupiter right out to the outer magnetosphere to where the boundary between Jupiter's magnetosphere and the solar wind is, and then back in. And this presents an incredible opportunity for us to link up the X-ray emissions that we see from the planet with precisely the physical processes that produce them. And we've been very, very fortunate with XMM and with Chandra to get some amazing opportunities where we have data sets when Juno's directly over the pole measuring the particles as they precipitate to generate emissions, and right out in the outer magnetosphere viewing the processes that cause auroral emissions and cause other emissions at Jupiter. So this data set's huge, it's so rich, and what I'm hoping to show you today is a tiny fraction of the amazing opportunities that it presents. And specifically, I guess, because it's a time domain conference focusing on Jupiter's periodic pulsations, these bizarre clockwork-like emissions that the planet produces, and the processes that it looks like from our comparisons between the X-ray data and the Juno spacecraft, what precise physical processes lead to these. So first of all, some context. So Jupiter's magnetosphere is the biggest coherent structure in the solar system. If you had some magical magnetosphere viewing eyes, you'd see a structure that was about 6 times the size of the moon across the night sky. So it's huge. At one end, it's at 5 AU, and right down at the tail of Jupiter's magnetosphere, it's at 10 AU. So actually, right now and for the next month and a half, Saturn is passing through Jupiter's magnetotail. So every couple of days, this magnetotail is wafting over the top of Saturn and blocking out the solar wind from Saturn, and then as the tail wafts back off it, the solar wind will hit Saturn again. So that's it's pretty crazy that we have this environment in the solar system where one planet's magnetosphere is so vast that it keeps bumping into another one's magnetosphere. Well, I say keeps, this happens every 19 years. But yeah, so that's something going on at the moment. So why is this magnetosphere so vast? What causes it? So one of the key processes is Jupiter's tiny little moon, Io. So Io is the most volcanic body in the solar system. Here you can see a GIF from the New Horizons spacecraft as it flew past, and you can see it throwing one of these volcanoes going off and throwing material 300 kilometers into space. And so Io is busy ejecting about a ton of material every second. And so as it ambles around Jupiter on its orbit, it leaves a trail of this material that forms this torus type structure. Whenever this neutral material that's thrown out by the volcanoes is hit by solar photons or collided with by other plasma in the environment, it ionizes it, and so you get all of this ionized plasma that's dumped into the system from the moon Io. And when this ionized plasma becomes ionized, it feels Jupiter's very strong magnetic field, right? At least, I guess in X-ray context, it's maybe not that strong a magnetic field, but on planetary contexts, Jupiter's tens of Gauss surface field is pretty strong. And so this plasma feels that tug of that magnetic field, and the combination of that with Jupiter's very quick rotation. So Jupiter's day is less than 10 hours. And so it's whipping that very strong magnetic field through space. And as it whips it through space, it picks up all of this material from Io and it accelerates it. And so what this does is it creates a space environment where you have regions that are dominated by the magnetic field of the planet, but also regions where you've heated up this plasma to the point where the plasma pressure is also a very significant factor in contributing. And so you get quite a diverse range of different environments around the planet where you'll get regions where the ratio of the plasma pressure, this hot plasma, is hundreds of times the magnetic pressure. And this presents lots of very interesting environments in terms of the natural laboratory. So I think Dennis talked about this already, that the solar system provides us with a lot of opportunities where we have local analogs and we have these local situations and environments where we can measure in situ and we can send spacecraft to them to determine precisely what physics dominates those environments, in order that then we can better understand all those vast domains across the cosmos where we can't actually visit them with in situ instruments. So Yeah, so Jupiter has this set of different environments, and the question is, how can we probe it? So right now, I've already said we're very fortunate to have the Juno spacecraft orbiting Jupiter. It passes over the poles, measuring the processes going on over the poles, close to the planet, and then zips out. This is probably a poor choice of graphic, but it zips out hundreds of Jupiter radii away from the planet, and then comes back in after its journey 100 Jupiter radii away from the planet every 53 days. And that lets us connect, hopefully, the remote signatures that we see from Earth with the physical processes that are producing them. And for today, I'm going to focus on the quasi-periodic pulsations. So in order to understand these pulsations and how they're connected, we need to go back 4 decades. So back in 1979, the Voyager spacecraft was first approaching Jupiter. And on its way to Jupiter, it saw these bizarre radio pulsations. So this is a spectrogram. We have time on the x-axis, frequency of the radio pulsations on the y-axis, and the color bar indicates flux or intensity of emissions. And so what you can see is these bright bursts of radio emission that seem to occur roughly every 10 minutes. After the Voyager spacecraft saw them, then Ulysses, on its way through like gravitational assist from Jupiter and then back to the sun, also saw these bursts of emission in the 90s. And then Cassini saw them as well, and then Galileo saw them as well. So there is some process at Jupiter that enables the planet to produce a pulse of radio emission about every 10 minutes, somewhere between, on timescales of tens of minutes. Another thing that Voyager discovered way back in 1979 was Jupiter's ultraviolet aurora. So these are the most powerful northern lights in the solar system. In fact, if you had some magical system where you could tap the energy that's produced by Jupiter's aurora, you could power all of human civilization with the northern lights. They produce crazy events like these terawatt flares. So this is where within a matter of between 30 seconds and a minute, the northern lights will produce these bright, hugely energetic events. So I heard someone say the other day that the problem with writing a thesis is that you're trying to turn something into, you're trying to turn your thoughts into something linear, and often in science, it's not that easy to turn things into something linear. So here I'm going to take a very quick detour to explore the structures in Jupiter's northern lights and to demonstrate what features occur there. So this is a video from Hubble. We're looking sideways on at the planet here, and here we've reprojected this sideways on view so that we're looking down onto the North Pole. And you can see there's lots of different things going on. I hope this video is playing okay, just over zoom. So at low latitudes, we get footprints from the satellites. So this little blue dot that you can hopefully see moving around the outside here. This is the footprint of the satellite Io. So as Jupiter whips its magnetic field through the environment, it drags the magnetic field over the moon of Io, and that causes bright auroral emissions. At slightly higher locations, we get these big injection events. So these last about a Jupiter rotation, and they're caused by what's called magnetic reconnection in the tail, we think, and that dumps lots of hot plasma into the system, and that leaves these big blobs that, that rotate. Then here at slightly higher latitudes, we have this main oval structure. So this is, this very bright and well-defined oval that sits here and kind of continues around with like a slight discontinuity here. This oval changes, we know it changes with solar wind conditions. So during events like coronal mass ejections, these big solar storms, when they collide with the planet, this thing will get very, very bright. And at other times when the solar wind conditions are quite dim, it will be very dim and slim. And then poleward of that, there are all these flares and swirls and very highly time variable signatures. I think it's fair to say that for the last 25 years, at every outer planet talk I've been to, people have said, we've no idea what causes those. But what I think is exciting about this work is that we've leveraged the X-ray emissions. And without the X-ray emissions, we really wouldn't be able to understand what causes these bizarre pulses and flares and swirl regions up here. So I hope that quick detour was okay. So again, just quickly, footprints of satellites, injection events, main emission, and mostly for the purpose of this talk, the polar emissions, which are all these crazy bright flares and things that are going on in the polar region. Right, back to 1979. So at the same time as the Voyager spacecraft was approaching Jupiter and measuring these bizarre quasi-periodic radio bursts, and at the same time as it was first observing Jupiter's ultraviolet aurora, the Einstein Observatory was taking the first X-ray images of Jupiter. And way back in April 1979, it first detected X-ray emission from the planet. This image is from 1991. It's a bit blurred. I'm sorry. I don't think there's a high-res version, actually, I guess, because it's from 1983. But you can just about see here that Jupiter's northern and southern lights from these very first Einstein observations. Chandra, obviously, and XM as well, completely revolutionized our understanding of Jupiter. It turned images that looked like this from Einstein into these very well spatially resolved images where you can really make out a lot of the substructure. Dennis has already mentioned that lots of bodies in the solar system depend on whatever the sun is doing. So this equatorial emission that you can see from Jupiter here, we see this vary with the solar cycle. So during this image here was taken at about solar maximum. And so you can see that it's very busy and full of emission. But during solar minimum where the sun is very dim in the X-rays, this emission across the equatorial region basically disappears. And what you get is a blank space of sky where the planet is blocking out the background. And then you get the aurora floating as these kind of ephemeral blots at each pole. If you're interested in the processes going on in the sun, then you can extract a solar spectrum from the disk of Jupiter at any given time, and that accurately represents whatever the sun spectrum looked like at that time. But for most of this talk, I'm going to focus on the polar emissions. Because, I mean, another great thing about Chandra is that we have not just the exquisite spatial resolution, but we also have timing resolution. And that lets us build whole maps of the planet. And so this is along the x-axis here, you've got lines of longitude for Jupiter, and along the y-axis, you've got latitude lines. The red contours are Jupiter's magnetic field, and then the color bar is the X-ray emissions, so the X-ray brightness that we get from the planet. This was made by Randy Gladstone. And so again, you can see the northern aurora and then the southern aurora, which is a little more diffuse, but you still get like a spot feature here. Once we build these maps, we can do what we did with the UV, and we can take these maps where they're, instead of a latitude and longitude grid, you can reproject them, and you can pick a place on the globe of Jupiter where you want to focus on. And so here, again, we've picked the North Pole, and we're looking down onto the North Pole. Prior to 2016, I guess, we only had one simultaneous Hubble and Chandra observation of Jupiter, and this is it. And so in orange, we have that UV main oval that I was talking about. That's this structure that sits like this. And then over the top of it are overlaid these green dots. So the big fat green dots, they're Bremsstrahlung emissions, so they're from precipitating electrons. And the little tiny green dots, they're soft X-ray emissions, so they're very much like Dennis was showing, they're charge exchange emissions. But I guess the thing that's very different here is that we don't actually think these charge exchange emissions are from the solar wind. We think these charge exchange emissions are that volcanic material that Io's been pumping out, raining down onto the pole of Jupiter. And so what we see in this paper from Graciela Branduardi-Raymond back in 2007 is a fit with XMM's RGS instrument data of oxygen charge exchange lines. And you can see that they're a pretty great fit to the spectrum. I think this, one of the key advantages of the X-ray instruments that they can offer over Hubble. So obviously with Hubble, we get these amazing, very photon-rich, spectacular videos of the aurora. But those videos are only 40 minutes long. And so if you want to explore how the aurora evolves from one observation to the next, you really need the timescales that the X-ray observatories offer. So tens of hour observations, which really let you measure how the auroral structures change from one observation to the next. The other thing is that the Hubble UV observations reveal emission from the atmosphere, so they're hydrogen emission from precipitating particles into the atmosphere. But the X-ray observations are revealing precisely the particles that are precipitating to cause that emission. So they're showing you the electrons as they precipitate into the pole here, and then the ions as they precipitate into the pole. So you're measuring actually the flow of plasma in the whole system. And I think that's kind of important for revealing the fundamental processes that dominate these systems. So this, to come back to these quasi-periodic pulsations, one of the crazy things that Chandra first observed Jupiter doing when it took those first observations back in 2000 was that it saw that Jupiter's aurora seemed to be pulsed with very regular periods, much like the radio emission was seen. So here what you can see is a 10-hour observation of Jupiter. You see that the northern lights of Jupiter come into view about here and then rotate back out of view. But also on top of that modulation as the aurora comes into view and then goes out of view, you can also see it pulsing. And so we see the aurora do this in most observations. It will produce pulsations rather than being kind of a steady emission. It's very sharply pulsed with these bright flares or impulsive emissions. Here I've just plotted a light curve with time on the x-axis and counts on the y-axis. And again, you can see these abrupt flare type events happening. Here on the right, I've just taken a Fourier transform of this light curve so that you can see at what cadence this periodicity occurs. So on the y-axis for the periodograms, we just have the strength of the signal essentially, and on the x-axis we have what period it's associated with. So you can see that this observation from the 1st of June here has a very regular pulsation rate at somewhere between 9 and 13 minutes. And what we see is that we see with 2 different instruments on 2 different days that Jupiter is exhibiting this bizarre 10-minute clockwork-like pulsation rate. So one of the key questions is, how do these signals relate? Are the radio pulsations that happen on these 10-minute timescales at all linked to the X-ray emissions? And how does the UV feature into this? Seeing that there are X-ray photons in locations where it seems like there are UV events, how do all the different wave bands stitch together? And these are questions that we couldn't really answer until the Juno spacecraft arrived at Jupiter, and until we got these unique opportunities to take images at the same time as we had in situ measurements. So here, just working with Nancy Walker at CFA, we've overlaid the X-ray emission from Chandra, so that's these purple aurora, on top of Juno's first visits to the North and the South Pole. And so these are the sorts of images that Juno can take, and we can start to connect what Juno sees in these locations on the North Pole and the South Pole with what processes produce the X-rays. So first of all, I'm going to talk about how we connect different wave bands. So these are synchronized X-ray and UV observations. What we've done here is we've just taken the aurora from poleward of that main oval, so that all the bright dynamic flares and things like that we saw. And we're overlaying the X-ray and the UV light curve, and what we see is that there's a pretty good agreement. And we see this in all the simultaneous observations, that the X-ray and the UV light curves exhibits what seems like very similar pulsations. If we take correlation coefficients between the 2 data sets, we see that there's a good agreement, and that there are strong correlations between the 2 data sets of between 0.7 and 0.8. But this raises the question, so what actual structures do connect the 2 wave bands? What processes where we see hydrogen emission from the atmosphere of Jupiter in the UV, how does that connect directly with what the X-ray sees as precipitating particles? And so to do that, I've overlaid X-ray and UV maps and turned them into videos, essentially. So again, we have a latitude and longitude here, just focusing on Jupiter's northern aurora. The color bar is the Hubble observation data, and the white dots are Chandra X-ray photons. And so what you see here is that there are actually several different structures in the UV and the X-ray that are interconnected. So we see these kind of diffuse emissions that stretch over here and form this kind of arc-like structure here. These seem to be shared structures between the UV and the X-ray. And then furthermore, there are the bright flare features. So these are these crazy terawatt type flares that go off on timescales of about a minute. And they also seem to be connected between the X-ray and the UV. So whenever we see a UV flare go off, we also see bright X-ray brightening. In fact, it seems like the X-ray pulsations that I showed before are the counterpoint or the counterpart of these UV flares. So where the UV observations only allow you 40-minute timescales, and that doesn't really allow you to probe quasi-periodicity that occurs on, say, a 20-minute timescale, because you're not going to see enough pulsations to understand it. The X-rays really let you delve into the details of this. So, okay, so a quick summary. So it looks like the UV and the X-ray emissions are connected via the flares and also via some diffuse structures. I'm going to focus on the flares because these are the bright pulsations we see that occur quasi-periodically. We can also connect the X-ray with the radio emissions. So these are Juno observations of those radio emissions. These kind of streaky-like structures that you can see here throughout are those same quasi-periodic pulsations that we've been seeing since 1979 with Voyager, and then we're seen with Ulysses, and then we're subsequently seen with Galileo and with Cassini, but of which we don't know the cause. And so if we take a slice through those pulsations in the radio data, that's what this dotted white line is here, and we overlay the radio intensity with the X-ray intensity, what we see is that the X-ray and the radio emissions seem to again pulse in time together. And so what this is suggesting is that there's a deep connection between the UV flares, the X-ray flares, and the radio pulses, and that all these quasi-periodic structures that Jupiter creates and bizarrely work like clockwork are connected between the wave bands. And there's some sort of synchronicity or some sort of rainbow of quasi-periodic pulsations. And this is just another example. So again, we have the bright pulsations here. This is another interval. And again, I've taken a slice through it and just overlaid the X-ray and the radio pulsations to see that they're interconnected. We see this through every Juno observation where we're in the right locations to see the radio emissions, and we have Chandra or XMM observations. We seem to see that the radio pulses and the X-ray pulses coincide within about a 1 minute window. So it looks like there's a connection between the two. To finally stitch it together, we have this fortunate event where we can create a short case study where Hubble observations show this bright flare go off just here in the south. And at the same time as this bright flare was going off in the south, the Juno spacecraft was flying through this region. And so we got in situ observations directly over the pole. And we also had X-ray observations at this time as well. So we can stitch together all three data sets to see what's going on. And what we see is that when this flare goes off, which is indicated by this dotted line here, we get a slight increase in X-rays. The problem here is the visibility wasn't great at this time. We see that the UV emission peaks as well at about this window. And we see that there's this bright burst of what's called Whistler modes. So there seems like there is a direct connection between the Whistler modes and radio emission, the X-rays, and the UV pulses. But the question, I guess the interesting question, if we were going to try to link the observations in the X-rays out to other processes that we see across the cosmos is, so all of these wave bands are connected, but how are they connected, and what process drives these pulsations and enables a planet to produce these crazy terawatt type flares? So during another interval, we were very fortunate to have magnetic field measurements at the same time as having radio and X-ray measurements. And so what we see is that, again, you see these quasi-periodic radio pulsations. Again, I've overlaid them on top of X-ray pulsations here. And then in the magnetic field data, we see these dropouts in the magnetic field that happen with the same periodicity as the X-ray and radio pulses. These dropouts are what are called compressional mode waves. And so they're waves that will work their way through the system and will perturb the plasma as they go. If we take a periodogram of the radio emissions and the X-ray emissions and these fluctuations on the magnetic field, then what we find is that for the radio emissions, the X-ray emissions, and the magnetic field, they all peak with precisely a 42.5 minute period. So these magnetic field pulsations that are happening out in the magnetosphere are occurring with exactly the same frequency as we see the emissions coming from the polar region. These are just further examples of this. So in every observation campaign, in every observation we had from 2017, we saw the shared behavior between the X-ray emissions and the magnetic field emissions, where we get the biggest spike in the magnetic field also coincides in periodicity with the biggest spike in the X-rays. And I think we're yet to find an interval where this isn't the case so far. And so it seems like the driving process for Jupiter's quasi-periodic X-ray emissions, their radio emissions, and the UV emissions is these compressional mode waves. But how do they do this?
3 minutes.
So, how long, sorry?
3 minutes.
Okay, great. Okay, so as these compressional mode waves work their way through the system, what they'll do is they'll perturb your plasma. And when they perturb the plasma, they're going to cause it to create anisotropies. So that's situations where the temperature of your plasma in one direction is no longer equal to the temperature in a different direction, in a direction perpendicular. And the plasma really doesn't like this. And what it does is it triggers resonances between the gyration of your electrons and your ions around the magnetic field line and the magnetic field line. And so these two populations will start to resonate. And what we'll see then is increases in certain wave structures, and we'll see frequencies in those wave structures that match with the gyro frequencies of the population. So Io is busy pumping out all this volcanic material. It's dumping sulfur and it's dumping oxygen into the system. So they're really the dominant components of the dominant ion populations in Jupiter's magnetosphere. And what we see is these cutoffs in the waves at precisely the gyro frequencies of sulfur and of oxygen. And so, and this is very expected. We see this, we see emic waves, these electromagnetic ion cyclotron waves driven by compressional mode waves. So when you get this compressional mode wave work its way through the plasma, it will trigger these resonances with the ion population. And what those resonances do is they drive the ions from out in this disk of plasma up towards the planet and along the magnetic field lines. They're really good at redistributing ions, but they're also really good at redistributing very high energy electrons. And so these compressional mode waves work their way through the system, trigger these emic waves. The emic waves trigger the particle populations to pulse, and those particle populations will be triggered to travel along the magnetic field lines towards the planet. And then very shortly afterwards, we see bursts of X-rays and we see bursts of UV and we see bursts of radio emission. And again, we see this throughout all of the intervals where it's possible for us to measure the emic waves, the compressional mode waves, and the X-rays for the observations where we've been able to study this so far. And so just to summarize, we've had this almost 41-year mystery of why Jupiter produces quasi-periodic pulsations. And I think we're finally getting to the root of it, what physical processes enable planets to generate incredibly powerful auroral flares, but also these quasi-periodic events. And it seems like what is going on is you have these compressional mode waves out in the magnetosphere. They interact with the plasma population through resonances with the gyration of the particle around the field line. Those resonances cause the particles to travel along the field line. And then at high latitudes, we see a conversion of the mode to generate the radio emissions. And then when they crash into the pole, we get these bright X-ray and radio auroral flares. I'll probably leave the talk there. So I hope that was clear, but if there's any questions, please feel free to ask, or if you'd like more details and more information, or if you think you'd like to collaborate on X-ray observations of Jupiter, then please don't hesitate to get in touch, or I'm on Twitter with 2 underscores with this handle. Thanks.
Thank you, Will. That was an excellent talk. Very interesting. Lots of stuff that you covered in there. If we have any questions from the attendees, we're happy to field those questions. I actually have a question for you before I go to the Q&A. It looked like in the magnetic field measurements, the magnetogram, that they were lagging the flares. So
it's actually the opposite way around. So okay. we have the magnetic field measurements are taken out in Jupiter's outer magnetosphere, and so then what we see is the flares occur. The problem here is the reason that it's essential to have the X-ray instruments for this is that it's very difficult to connect single events together because the distance scales are so big. So you have Juno measuring events at great distances from the planet, and then the auroral response. And really, you need really long time scale observations to be able to see the connections, for instance, in these unique periodicities. And I think that's essential, and it's why probably other wavebands haven't been able to do this before, and why the X-rays are giving us all these cool new insights, because we have these long time scale observations where you can say, okay, we can't connect one-to-one this flare with this compressional mode wave, but when we see compressional mode waves happening every 20 minutes for 6 hours, and we see the X-ray flares going every 20 minutes for 6 hours, it's kind of, it feels like a smoking gun that the two are connected. Does that help?
Yeah. Okay, we have a question from Brad Sinos. If you had higher X-ray sensitivity, would you expect to see an energy dependence in the quasi-periodic X-ray emissions?
That's a really interesting and challenging question. Thanks, Brad. Yeah, so I think what you would expect to see is, yes, you would expect to see, basically when you see these emic waves, I think what we would expect to see is the cutoffs of the emic waves indicate their interaction with different particle populations, right? So you can see that this emic wave here cuts off at the sulfur plus frequency. So it's probably less likely that that interacts with the oxygen population, and it may not interact as much with this is a bit hand wavy because I haven't thought about this enough, but it may interact less with, let's say, the MEV electron population, or it may interact more with KeV electrons than MEV electrons. Equally, the flip of that, where an O double plus emic wave may interact more with oxygen ions and less with KeV electrons due to the resonances around it. So what I think you might expect to see is, depending on the type of ion cyclotron wave you get, you'd see different charge exchange lines from the precipitating particles. Yeah, so yes, that's a really cool idea. And I think if we had more sensitivity and we could look at the spectrum on timescales of single flares, we might be able to see, for instance, the oxygen charge exchange lines triggered by certain types of ion cyclotron waves, and the sulfur lines triggered by other types of ion cyclotron waves, and the Bremsstrahlung emission triggered by other types of waves, like the Whistler modes or something. I hope that helps.
Great. Any other additional questions? I think I'd like to also pose to you the question. Let me get to this one first. This is from Gayatri Raman. Can you reconstruct the size of the pulse emission regions in the northern and southern auroras from the pulse profiles, X-ray or radio?
So size is in spatial scale. I think that would be quite difficult because with XMM, for instance, we have the better sensitivity, but we don't have good enough spatial resolution to resolve the flares. With Chandra, we have this amazing spatial resolution that lets us connect the UV and the X-ray emissions. But what we can't do, but we don't get enough counts to say probably the size scale of the X-ray flares. You could probably do it by analogy with the UV maybe, and you could use the spatial scale of the UV flares to connect. Or maybe, I mean, this is something where links will be a complete game changer. If we get links, it will be incredible for this type of stuff, because it will take these like single X-ray photon events, and instead it will turn the X-ray aurora into something that looks like the UV aurora, but we'll be able to do it on timescales of hours and hours. And so I think, not to push it back 10 years, but links would be will give us a complete paradigm shift in how we can do this science. I think the problem again is that we're photon limited. So it would be difficult for us to say the difference between one X-ray flare and another X-ray flare could be 6 or 7 counts to 12 counts. And so there you're looking at differences where you're probably dominated by the Poisson errors. Over timescales of tens of hours, sorry, this is really waffly. I think you could probably do it with generalized observations, where if you have one set of observations where your X-ray pulses are really bright, and another set of observations where the X-ray pulses are really dim, then probably. But in terms of one pulse to one pulse connections, I think again it's difficult because of the limited photon counts. Until links.
Until links. Okay, I have a question for you. It's related to the one that was brought up before. Obviously, in the eROSITA sky survey, Jupiter must be in there somewhere. What do you expect from that?
Okay, so this is going to showcase my ignorance, I think. I don't know enough about eROSITA, and I'd be really, really keen to work with anyone working on eROSITA to try and to see what we can see and to determine what extra science we can gain out of it in terms of Jupiter, and maybe Saturn or Uranus or yeah, right, or Mars or Venus or whatever. Yeah,
right.
So I don't know, and that's entirely through my own ignorance, and I'm sorry for that.
That's okay. I'm sorry putting you on the spot. You mentioned links. Any additional questions? If not, any questions for any of our speakers today? And Conrad General, if you want to speak, let me know. You can tell us about eROSITA and comets and planets. I think it's been on everyone's mind.
Okay, can you hear me?
Yes, we can.
Ah, great. So because eROSITA was mentioned a few times, The last question, actually, Jupiter was observed by chance with eROSITA, but the problem is eROSITA is not designed for these optically bright objects, so we got a lot of optical loading, and that was it basically. And now eROSITA is doing all-sky surveys. This means that the exposure time is very short for an individual object. I don't expect much progress in science from for Jupiter, similar to Mars. This is also the problem is the optical loading.
Right, of course.
And the other earlier question was
problem for Saturn and Uranus, correct?
Sorry.
With I guess that same problem would exist for Saturn and Uranus, right?
Well, optical loading is less, but I think it's hopeless. I mean, even with XMM to detect X-rays from Uranus, you need hundreds of kiloseconds, I would expect. So they're really faint X-rays. Jupiter is a outstandingly bright counterexample.
All right. Thank you very much for that feedback. Do we know, Will, if Lynx will have an optical blocking filter, speaking of the challenge?
Oh, I don't know. I hope so. I really hope so, for all the reasons Dennis said.
Right.
And because of everything Conrad just said. Otherwise that all my science hopes and dreams for Jupiter's aurora.
Right.
It's a little bit ironic that exactly the optical blocking filter causes the problems for ACES now.
Yeah. I mean, imagine ACES observations of this stuff. I'm amazed you're still able to do comet observations. It's really cool with ACES because, yeah, if we could bake it off, then yeah, the possibilities.
Okay, if no more questions, I think it's time to wrap up this session. I'd like to thank everyone again, all the speakers, for excellent talks on solar system objects. I think that was riveting and quite interesting and really showcases all the stuff that Chandra can do, spatial, spectral, and timing. So thanks again. I hope you join us later on in about 30 minutes for our next session, which is a panel on communication and coordination amongst ground and space-based observatories. Thank you all for joining and have a good morning.